Okay, so previously we had already, can you hear me? Hello? Hello? Can you hear me? Yeah. So previously we had already talked about the critical state line and basically the yielding surface, how to determine the yielding surface. And we established that in fact the yielding surface is the line from projection, of course, projected the line between the isotropic virgin consolidation line to the critical state line, which is a curve that forms the elastic wall, but the projection of that line on the QP space, that becomes the yield surface, as you can see in the illustration. Okay. So next, because like I've said, at the end of all this, all we interested in is how we use this in the numerical analysis to solve our problems. So just to show you that the theory for example analyzing materials that we use is actually based on very sound theory. The models are based on sound theory. So what we are going to enter into now is the description of what we call the Chemclay model. So the Chemclay model, so can you hear me? Okay. So so I think we already described this, how to the yield surface, the plotting on the EPQ space, the relationship to the 1D consolidation stress, and of course when we project the line EX to line E prime X prime, that becomes the yielding surface. And if the state boundary is known, then of course we can derive the yielding function. So we're ready to say this. So based on what we have described, then these two authors, Roscoe and Boland, in 1968, have the equations for the state boundary surface. Now this has been used to describe what initially was called the Chemclay model, one of the models in Plaxis. Initially it was the Chemclay model, but eventually, of course, and this is what I always told you, that we come up with some models that can describe something, but of course there's always a limitation, and then we always figure out that there's something better or something to be improved in the model. So initially the Chemclay model, and then became the modified Chemclay model. But the whole point, basically, this is based on the critical state line, the theory we've just talked about in detail. So the equation, so you can see in the theory we talked about P, we talked about PE, and the definitions you should remember. We talked about the M is the gradient of the critical state line, the Q and the P, Q being the deviatoric stress, P being the mean effective stress, and then the K and the alpha, the K and alpha, they found from uh, the 1D consolidation test. um, um, uh, when the horizontal axis is expressed in a log scale, in ln scale, sorry. Okay, you remember that? So these are gradients of either the virgin consolidation line or gradient of the unloading reloading. You remember that? And so this is how to determine E. Okay, and So these are basically, the point is, these are could basically be determined from the, once you know the 1D consolidation test, then all these things can be determined. And also this to buttress the point that you need to know the theory, so that from the tests, once you do the test, then you know what to do with the test. So usually the curve for 1D consolidation is like that, and this is the log ln of p. And remember we said PE is when, so just to refresh your memory, EA, so EA is when P is 1 unit. So it comes up, it comes back here, sorry, and then PE is so the alpha is the slope of the EP, then the kappa is the coefficient of unloading reloading. So, and what I wanted to explain is the PE. So PE is the, so you know this this curve, and then remember EA. So EA is somewhere when P is 1. So when this value is 1, when the value is 1, then you have EA. That becomes, that specific value becomes EA. So this PE can be determined from, so you, if you have any other point, so say E, that E, so this becomes EA. Remember, is when P, the value of P is 1, okay? So then you know EA, and that is E, and then lambda is the coefficient, so you can determine the value PE. So basically just to say, or to express that once you do the experiment, how you can relate then the experimental input to the experimental values, or how you can determine the software input or the model input from experimental values. So that is the point we're trying to demonstrate here. And that the, so from here you can see the yield equation. So you can rearrange. So if this one, because the yield equation is when the value is Q naught, so P when so just you can see here. So instead of having P, we can have P naught, okay, and the value of Q is 0, and therefore the you rearrange this equation and then become your yielding equation. So what I want you to relate is the yield equation from the, you understand? Can you see that? And remember that P naught is the value when P is P value is the P value when Q naught equals 0, okay? So when, with the yielding equation given above, we can then obtain the constitutive law for the Chemclay elastoplastic model. So that when you go now to the software or the Plaxis, you're trying to use either Chemclay or modified Chemclay model, you know, and confident that actually is based on very sound theory. But over and above that, then these are formulas we have talked about. So from here you can manipulate. So this is the yield equation, and we can, from the yield equation we can obtain the elastic constitutive law. So what's important for our materials is to be able to establish constitutive laws that can actually determine, or that can actually fit the behavior we see in reality. So all these parameters, D, dP, we know already, because the first thing you know, the relationship between stress and strain. So this is the stress, that is the strain. Once you are uploading your material, it's gonna deform. So from there we can get strain, and then this D is a deformation matrix. Okay, deformation matrix, and when you see P there, means there are they're related to the plastic. So the so the parameters related to the state boundary condition, boundary surface or the surface are M, lambda, and kappa. That's if the chemical model adopts the yielding equation. In me, the D is the deformation parameters such as E and omega, and so for the chemical model, they need the E, the mu, and with the additional extra input parameters, which is M, lambda, and kappa, which you should now be confident where they come. So now, you did not tell me you are not able to successfully install Plaxis. Is this what you are saying? No, but I've done it. The same one I gave you is in here, isn't it? You've seen me open it. So there's something you are not doing correctly, and I don't think I'm in the. I want to uninstall mine just to demonstrate to you that it can install. Let me finish, and I try, because now that we are talking about ChemClay, you should actually be able to at least use it to get the point across. So the behavior under isotropic compression. So this is the same thing. So we have just extended the margin consolidation line. Where is the so this usually we can plot the E and the void ratio, or it doesn't matter because the void ratio of course is a function of the volume, isn't it? So the margin consolidation line, the kappa is the gradient of the unloading reloading. The lambda of course is the gradient of the virgin consolidation line. So then for unloading reloading, we expect the gradient to be the same. So whether you unload from point B or point D, that's the same. But I have to stress that we have just extracted the linear part, the complete part of the complete curve is like that. So the virgin consolidation line swelling, we said that, and so you remember. So this is just saying what we have been talking about. So for the to get the to transform the yielding function to what did we call it? The plastic potential surface equal to 0, isn't it? Yeah. So this is, I told we originally have ChemClay and the modified ChemClay model. So that's, and we always said these functions are these equations are functions of the stress, and K, which are material parameters. So you can, I hope you can see that, because P and P of course the stress, and then the M, J are the material parameters. Okay, and so that's the yield surface. The yield surface. So if you were to plot J, L, and P, log of P, and the volume in terms of 3D, that would be your virgin. So this one extracting just this part alone. So we project, we draw in a 3D surface, and this is what we this is the result. Okay, that's how the yield surface would look like. So this is the modified. This is the initial proposal of the ChemClay model, and this is the modified ChemClay model. So you can just notice the differences in the shape. This was just a minute. Okay, so you can see the differences in the shape, the modified ChemClay model, and this was generally used to describe the failure or the yield surface of soil, because it's always thought that the yield surface of soil is an oval shape. If you have to draw in a PQ surface, so this is Q, this is P, it's always thought is an oval shape. So this was the best attempt to describe that oval shape, but people realized that differs significantly from what is observed. So then it was modified again. People thought this is more, describe it more closely. Okay. Of course, still there are gaps. Is still very difficult. This is what we observe. So you can see now, even when we are saying that is modified, it just plots in a different. Just plots. It's still different from what we observe in practice. So that's the modified ChemClay model. Okay. Of course, still gaps. Still a lot of research required to find. So this ChemClay maybe can describe the yield function of certain soils, but definitely not all of them. Okay. And so the ChemClay model is actually isotropic, kind of symmetric around the p-axis. Okay. So as noted above, behavior along swelling line is elastic. This means that the elastic volumetric strain can be determined from the equation 7.35. Yeah, so you can differentiate this equation to get the incremental elastic strain, volumetric strain, and yeah, I hope you did not forget how to differentiate, isn't it? You know this line. If you differentiate, ln is 1 over something, isn't it? Yeah, so please, I hope you be able to figure out. So this is how to get the incremental volumetric strain, elastic volumetric strain, because that's an elastic behavior, and that's the state boundary surface, where K, of course, is the elastic bulk modulus. Remember, we talked about this at the start of this course. So basically, to relate the software input to what we can easily measure in the laboratory. So if you want to get the K, we know K, then you know the P, isn't it? And then you know this relationship. You can easily get the incremental. You know this relationship, so you know Kalpa you can measure, K can be measured, or even if you don't know, you know that relationship you can determine, because the stress, Kalpa you can measure, you can determine those other things. In any case, K is usually a constant for certain materials. Bulk modulus, for example, for water or for soil or for something else is different, and we know the range. Okay. Then the volumetric behavior of ChemClay soils. I've said. So we start by this one. If you talk about the incremental elastic or plastic strain, you find it should be 90 degrees to this surface, isn't it? Now, in this side, we show the dilatant behavior, because you can see if we resolve this a vector, if we resolve it, you can see this is negative, everything is negative, so that shows dilatant behavior. Okay, that especially the volumetric behavior is dilatant on this side, and then on this side you resolve this vector, then the incremental behavior is compressive. So dilatant maybe would mean tensile, isn't it? And this is compressive. So this is dry or supercritical softening, so on this side, and the other side is subcritical wet or subcritical hardening. Okay. Then definition of critical state, I think we already talked about this. The final state of soil samples in triaxial test, when it is possible to shear the sample with no change in post stresses or volume of the soil. So please note this important. So when you can shear the soil is a triaxial condition when it is possible to shear the sample with no change in stresses or in volume of the soil. Remember, shearing is usually associated with volumetric change, isn't it? So that is the definition of the critical state. Okay, so the okay, now we draw or an explanation or illustration basically of this where the uh, curve, for example, the first one is of J, and you should know the definition of J and strain. Okay, so one for volumetric strain, the arc strain, and this is strain axial test. NC is normally consolidated, and also means consolidated. If you remember, we have talked about that several times. Okay, so these are the drain separation tests with modified MP model. Now, because now you are seeing this and you cannot relate. This is why I wish you would have installed the software successfully, so that uh, you can indeed reproduce at least one of these curves, so that you can easily relate to what we are talking about. I'll try my best. I'm not willing to uninstall my Plaxis just to demonstrate. There's something you are doing wrong. I'm wondering what it is. You see the same file I gave you. Are you there? It's the same file I used to install, and mine is working. So how come yours is not working? It's a very file. So that's undrained, and so normally consolidated and over consolidated. So maybe so this is what I wanted to show you. So remember I told you of the dilation behavior of sands, isn't it? That for so no, this is what I wanted to want you to see the difference. So generally the behavior observed is that dense sand and over consolidated clay almost behave the same way. So dense sand, remember this is the same thing I described. For dense sand we reduce, and then the volume reduces before we have a constant volume. And then soft clay, again, just like loose sand, behaves like loose sand. That's what has been observed. So the same thing here, you can see over consolidated clay, there is a reduction to a minimum volume, then dilation, and then a constant volume. However, for soft, normally consolidated or soft clay, just reduces to a minimum value, and that's it. Okay, so the soft clay usually behaves more or less like loose sand in terms of volumetric change during shearing, and then over consolidated clay behaves more or less like dense sand in terms of the shear volumetric behavior under shear. Okay, and then extension of the general stress space. So this one, this theory you know very well. We've talked about the Tresca, the what? Tresca, which other one? Von Mises and all those things. Yes, yes. So again, now we add other theories. So if you draw this in sigma 1, sigma 2, sigma 3 space, so these are the other failure surfaces in the deviatoric plane as different, as per different authors. So more Coulomb, then we have the circular one, then lead. So these are different authors trying to produce failure surfaces in the deviatoric plane. Of course, the backbone upon which they ride is a theory which we've laid down so well. Okay, the von Mises, the Tresca, and so on. So they try to make some improvements to just see that these yield surfaces agree with what we see in actual material. So different authors there, and the plots, as you can see. So this also buttresses one thing, that so whenever you come up with something new, it's always good to benchmark it with what is existing. You understand? So you learn this a lot in probably in your research. So if you were coming up with something new in an area that other people have done, so it's always good to do yours and then compare with what other the existing, so that we can clearly see. Because one of the justifications for doing that, you'll say maybe yours is giving a better prediction, or there is some edge that yours is having over this other, and then when you put them together, it's easy to see. Okay. So in order to obtain more Coulomb hexagon for the yield surface in the deviatoric plane, MJ in equation 7.36 and 7.37 must be replaced by G theta, and this is the definition of G theta, where phi CS is the critical state angle of shearing resistance, which replaces MJ as an input parameter. This expression gives the hexagon shown. So this is how we have come up with hexagon we've just shown you in the more Coulomb theory, and this equation. So this is the original form of the equation, isn't it? So with what we have said, so you can see the transformation. So the equation is 7.36 and 7.37 transforms to 7.42 and 7.43. So in terms of Matsuoka and Nakai, surface can be expressed. So just I told you that all this is riding on the theory which we've laid down. Okay, and now this is just explaining what has been done to get. So this is for the more Coulomb, but in terms of the Matsuoka and Nakai surface, this is their definition. So this can be obtained from specific value of Lord's angle. Now you see why we were talking about Lord's angle. We already introduced Lord's angle, isn't it? So by solving the following cubic equation, we find that specific value of the Lord's angle, and where mj is the gradient of the critical state line in JP space corresponding to triaxial compression, where theta is minus 30 degrees. In terms of the critical state angle of shearing resistance in triaxial compression, mj in equation 7.45 can be, so that's how to determine the nj can be expressed. So and here we take that value at specifically when phi cs is phi cs when that angle theta is negative 30. Okay, so the lead surface can be expressed by, so just showing you, this is just an explanation of how these have been plotted. So we've talked about how Mokulumb hexagon has been found, how Matsuoka Nakai surface has been found, and you can see for yourself then how the leads, okay, the leads solution, okay, and okay, so is that all we have? Then the undrained strength for chem clay. Don't worry too much. The theory, I need you to understand the basis of the theory, okay? Otherwise, in the exam, what will be brought to you is something you can easily do. And if any of these equations is required for you the equation will be provided. Is only for you to understand the basis of what we are saying. Okay, so for the ChemClay model, so this is undrained shear strength for the ChemClay model, and for the modified ChemClay models, okay. Then modifications of the basic formulation of critical state models. So like I always said before, we are always trying to see the best of these models that can fit what we find in or the natural soils or the natural materials that we have. So this is the critical state line for ChemClay, but you can see Hovslov came up with certain modifications, and this is for lower chromatin. So this one they used this kind of soil. Yeah, so there will be some variation. The best we can do is usually find a good estimate, okay? And this was the critical state line, but Hovslov found that there is some little variation, and try to come up with something closer to the behavior of the soil they were describing. But you can see now even him, he has plotted his and also what is existing, isn't it? So we can see that what is giving us is actually plots much better or closer, okay. But you can see now they use a very specific kind of, so this is this kind of soil. So this the surface is for that very specific kind of soil, okay. So this is why, and soon, I don't know if you have been told to do a write-up for your proposal. Have you? Yeah, already. So this is what we are looking for, the novelty that we are looking for in research, that there are gaps, okay. So what you are doing should add value, or add at least some information that we did not know before, okay. So this is why it is not acceptable to do what other people have done. But if you're using the same, if you are doing what other people have done but using another method, okay, can be accepted as long as that method is giving us either more accurate information, or that method is simpler, because we are always looking to make things simpler and do not take a lot of time. Okay, so what to look out for is something new. Yes, if you are using what other people have done or a different method to do the same thing other people have done, is that method simpler, easier? Okay, does it give us better results? Okay, so that just giving you an idea of the expectation. So you can be sure that all these things have been results of research, a postgraduate. Maybe this one I think could be a PhD, maybe modified. The one who came up with ChemClay probably was pursuing their PhD, and Hovslov probably. So that's how. Sorry. Yeah, the Cambridge. But usually these ones are okay. If it's not a PhD, maybe it's the what the. Usually the universities have groups of research, okay, under one professor. So maybe this is what they were working. But one thing you can be sure, in that group, a few people got PhDs based on this work. Okay, and so that's the Hounslow surface. I think you read basically what we are saying. So, and I think that we are done. So we are done with this. Have you seen this one? Yeah. Now to the big issue, the elephants in the room. I don't know what magic you're trying to do, but the file I gave you, um, I don't know how to help, but let me try.